Okay, let us continue the second part of today's class. Okay, in the first part of today's class, we have talked to this point. Okay, since that is because slowly varying channels have narrow Doppler spectra, that is small Doppler bandwidth, okay, which is BD. Then the coherence time and Doppler spread are inversely proportional to one another. Okay, so we have shown that for a time invariant channel, okay, the Doppler spectrum is a delta function, okay, which means that the Doppler bandwidth is equal to 0. Okay, so for slowly varying channel, Doppler spectrum is very narrow. Okay, that is Doppler bandwidth small. Okay, and the coherence time and the Doppler spread are inversely proportional to one another. Okay, so why? Okay, let us see this figure. Okay, because the coherence time is the width of space-time correlation function phi c of delta t, and the BD Doppler spread is the width of the Doppler power spectrum SC of V. Okay, and they form a Fourier transform pair. Okay, if you have learned Fourier transform, you should know a property of Fourier transform. That is, when the width of a signal in the time domain is wider, okay, then the width of the signal in the frequency domain is narrower, okay, and vice versa. Excuse me. Okay, so that is Tc is proportional to 1 over Bd, okay, where Tc is the coherence time and Bd is the Doppler spread. A conservative measure of the coherence time is the so-called 50 percentile value, denoted by Tc50, which is defined as the time separation for which the time correlation is equal to 0.5. Okay, it can be shown that, okay, in reference 61. Okay, let us see reference 61. Okay. Okay, reference 61 is a book which is written by Theodore S. Rappaport. The title of the book is Wireless Communications, Principles and Practice, 2nd edition. Okay, the publisher is Prentice Hall, and the book is published in 2002. Okay. Okay, so Tc50 is approximately 9 over 16 pi times Bd. Okay, so next let us see section 4.5, classes of multipath channels. In the previous section, we talked about the intrinsic properties of multipath channels. Okay, include 4 quantity. Okay, delay spread, coherence bandwidth, and the Doppler spread, and coherence time. Okay, there are total 4 intrinsic properties. In this section, we talk about how to categorize channels based on the relationship between these intrinsic properties and the nature of the signals being transmitted through them. Okay. Okay, here then means the channels. Excuse me. This results in the following four classes of multipath channels. First, flat fading. Second, frequency selective fading. Third, fast fading. And fourth, slow fading. We consider each of these types of channels in the following subsections. Okay, so first let us see section 4.5.1, flat fading. Okay, definition. A channel is said to be flat if the bandwidth of the signal W is smaller than BC, okay, where BC is the coherence bandwidth. It implies that TS is greater than Tm. Okay, TS is the symbol duration. Okay, and do you remember what is Tm? Okay, let us review it. Okay, let us find the meaning of Tm. Okay, Tm. Okay. Okay, Tm means the delay spread. Okay. Okay, so let us go back to the slide. Okay, it should be here. Okay, good. Under this condition, equation 4.12 indicates that. Okay, let us see equation 4.12. Excuse me. Okay, in equation 4.12, it is straightforward to show that R of t. Okay, what is R of t? Let us review it. Okay, so R of t is the received low-pass equivalent signal. So it's equal to the integral from negative infinity to infinity, and capital C of Tf, where capital C of Tf is the Fourier transform of small c of t tau. Okay, and okay, what is small c of t tau? Okay, do you remember? Okay, let us see. Okay, c of t tau is the linear time variant LTV impulse response function. Okay, and capital U of f. Capital U of f is the Fourier transform of small u of tau. Okay, and what is small u of tau? Okay, let us see the meaning of small u of t. Okay, good. Small u of t is the low-pass equivalent input to the channel. Okay. Okay, times exponential j2 pi ft df. Okay, this is equation 4.12. Okay, let us go back to maybe page 160. Okay, not this page. Okay, this page. Okay, so equation 4.12 indicates that R of t is equal to integral from negative infinity to infinity, capital C of t0 times capital U of f times exponential j2 pi ft df. Excuse me. Okay, and this equation is equal to capital C of t0 times small u of t. Oh, this equation number is in the wrong place. Let me correct it. It is strange. Okay, let me try again. So I add a sharp symbol here, and I type the math option and professional. Okay, the equation number should align to the right. Okay, so let us forget it and continue. Okay. Okay, so how do we derive this equation? Okay, because capital C of t0 does not depend on f, frequency f. So for this integral, capital C of t0 is a constant and can be moved out of the integral. And the remaining terms are integral minus negative infinity to infinity, capital U of f times exponential j2 pi ft df, okay, which is exactly the inverse Fourier transform of capital U of f. Okay, so it is equal to small u of t. And I think you must have a question. Why is the frequency f becomes 0? Okay, let me explain it. Where we have made the approximation that capital C of tf is equal to capital C of t0, since flat fading implies that W is smaller than BC, okay, that is signal bandwidth is smaller than the coherence bandwidth, which means that the channel is approximately constant and equal to capital C of t, f is equal to 0 over the bandwidth of the transmitted signal. Okay, so equation 4.40. Okay, let us see equation 4.40. Okay, so is this equation? We have seen this equation just about 2 or 3 minutes ago. Okay. Okay, equation 4.40 shows that under flat fading, the effect of the channel is a simple multiplication of the transmit signal by a complex gain. Okay, let us see this equation again. So finally, in equation 4.40, the received signal R of t is equal to U of t, okay, which is the transmitted signal, times capital C of t0, okay, where capital C of t0 is the frequency response at f being equal to 0. Okay, in general, capital C of t0 is a complex number. Okay, so we can treat this as a complex gain multiplied by U of t. Okay, so it is a complex gain. Okay, next, consider time to be discrete, where tk denotes the time at which the case symbol. Okay, S of k is defined as U of tk. Okay, we use the brackets to denote that this is a discrete time signal is transmitted, and define the channel response at that time to be h of k, which is defined as capital C of tk0. Okay. So it follows that R of k is equal to h of k times s of k, where R of k is defined as R of tk. Okay. If we now consider the addition of noise Z of k, then we can express the system model for flat fading as follows. Okay, R of k is equal to h of k times s of k plus Z of k. Okay. It should be emphasized that the expression in equation 4.41. Okay, let us see equation 4.41. Okay, is this equation just on the previous page? Okay. Okay, equation 4.41 does not impose any constraints on the variances of the individual terms. Okay, that is, you cannot see any constraints on the variance of R of k, or the variance of h of k, or the variance of s of k, or the variance of z of k. Okay. If, however, we use the conventions defined in equations 3.2 to 3.5, okay, let us look at equations 3.2 to 3.5. Okay, so everyone, please open the slides of chapter 3 and turn to page 9. Okay, so here are equations 3.2 to 3.5. Okay, first, the expectation of the square of the absolute value of hij prime is equal to 1. Okay, what is hij prime? Okay, it is the ijth element of the random matrix capital H prime. Okay, and what is the capital H prime? Okay, let us see the definition. Okay, capital and bold H prime is the NR by NT normalized channel matrix, where NR is the number of received antennas and NT is the number of transmit antennas. Okay. And the square of the forbinions known of H prime is equal to NR times NT for fixed H prime. Okay, and the expectation of the square of the absolute value of Zi. Okay, what is Zi? Okay, Zi is the ith element of the vector Z. Okay, and Z is the NR by 1 noise signal vector. Okay, so this is defined as sigma square and is equal to 1. Okay, this is equation 3.4. Okay, and the expectation of the square of the absolute value of Si. What is Si? Excuse me. Okay, Si is the ith element of the vector S, and S is the NT by 1 transmit signal vector. Okay, which is defined as sigma S square and is equal to 1 over NT. Okay, this is equation 3.5. Okay, let us go back to chapter 4. Okay. Okay, equations 3.2 to 3.5 for convenience in modeling. Then equation 4.41 becomes, okay, let us see equation 4.41. Okay, this equation, okay, which we have seen this equation about 5 minutes ago. Okay, so becomes r of k is equal to the square root of rho times h of k times s of k plus z of k, where rho denotes the signal to noise ratio. Okay. The MIMO form of this equation follows directly and is equivalent to equation 3.1. Okay, let us see equation 3.1. Okay, here. Okay, and in the page, on page 6 of the slides of chapter 3. Okay. So to understand the implications of these assumptions, okay, we have explained the assumptions, okay, in the above. We start with the following version of the MIMO system equation. R is equal to the square root of rho times h prime times s plus z. Okay, where r is the nr by 1 received signal vector. Okay, and h prime, s, z, and rho, we have explained them. Okay, so let us go back to chapter 4. Okay, so the preceding discussion provides a justification for that equation. Okay, here that equation means equation 3.1. Okay, next let us go to section 4.5.2. Okay, frequency selective fading. Definition: a channel is said to be frequency selective if the bandwidth of the signal W is greater than BC, where BC is the coherence bandwidth. It implies that TS is smaller than TM. Okay, what is TS? Let us review it. Okay, here TS is the symbol duration. And Tm is the delay spread. Under this condition, we seek to derive an expression for the received signal in terms of the transmitted signals, the impulse response of the channel, and the noise at the receiver. Okay, that is, we seek a system equation for a frequency selective channel that corresponds to equation 4.42 for flat fading. Okay, let us see equation 4.42. Okay, is this equation. Okay, let us see. Okay, R of k is equal to the square root of rho times h of k times s of k plus z of k. Okay, that is, the received signal is equal to the square root of SNR times the channel coefficient and times the transmitted symbol or signal plus noise. Okay, so let us go back to here. Okay, equation 4.42 for flat fading. We begin by defining U of t to be a band-limited, low-pass equivalence signal with bandwidth equal to W. Okay, it follows that such a signal can be expressed as an infinite sum. Okay, which is in, you can refer to reference 58. Okay, let us go to reference 58. Okay, it is 25 minutes. Let us take a break.